A natural nuclear fission reactor is a uranium deposit where self-sustaining nuclear chain reactions have occurred. This can be examined by analysis of isotope ratios. The existence of this phenomenon was discovered in 1972 at Oklo in Gabon, Africa, by French physicist Francis Perard. The conditions under which a natural nuclear reactor could exist had been predicted in 1956 by Paul Kazuo Kuroda. The conditions found were very similar to what was predicted. Oklo is the only known location for this in the world and consists of 16 sites at which self-sustaining nuclear fission reactions took place, approximately 1.7 billion years ago, and ran for a few 100,000 years, averaging 100 kilowatts of thermal power during that time. History. In May 1972 at the Pierre-Latte uranium enrichment facility in France, routine mass spectrometry comparing UF6 samples from the Oklo mine, located in Gabon, Central Africa, showed a discrepancy in the amount of the 235 U isotope. Normally the concentration is 0.72%, while these samples had only 0.60%, a significant difference. This discrepancy required explanation, as all civilian uranium handling facilities must meticulously account for all fissionable isotopes to assure that none are diverted for weapons purposes. Thus the French Commissariat à l'Énergie Atomique began an investigation. A series of measurements of the relative abundances of the two most significant isotopes of the uranium mined at Oklo showed anomalous results compared to those obtained for uranium from other mines. Further investigations into this uranium deposit discovered uranium ore with a 235 U concentration as low as 0.44%. Subsequent examination of other isotopes showed similar anomalies, such as neodymium and ruthenium as described in more detail below. This loss in 235 U is exactly what happens in a nuclear reactor. A possible explanation therefore was that the uranium ore had operated as a natural fission reactor. Other observations led to the same conclusion, and on September 25, 1972, the CEA announced their finding that self-sustaining nuclear chain reactions had occurred on Earth about 2 billion years ago. Later, other natural nuclear fission reactors were discovered in the region. Fission product isotope signatures. Neodymium and other elements were found with isotopic compositions different from what is usually found on Earth. Subtracting the natural isotopic Nd abundance from the Oklo Nd, the isotopic composition matched that produced by the fissioning of 235 U. Ruthenium. Similar investigations into the isotopic ratios of ruthenium at Oklo found a much higher 99 Ru concentration than otherwise naturally occurring. This anomaly could be explained by the decay of 99 Tc to 99 Ru. In the bar chart below, the normal natural isotope signature of ruthenium is compared with that for fission product ruthenium, which is the result of the fission of 235 U with thermal neutrons. It is clear that the fission ruthenium has a different isotope signature. The level of 100 Ru in the fission product mixture is low because of a long-lived isotope of molybdenum. On the timescale of when the reactors were in operation, very little decay to 100 Ru will have occurred. Mechanism of the reactors. The natural nuclear reactor formed when a uranium-rich mineral deposit became inundated with groundwater that acted as a neutron moderator, and a nuclear chain reaction took place. The heat generated from the nuclear fission caused the groundwater to boil away, which slowed or stopped the reaction. After cooling of the mineral deposit, the water returned and the reaction started again. These fission reactions were sustained for hundreds of thousands of years, until her chain reaction could no longer be supported. Fission of uranium normally produces 5 known isotopes of the fission product gas xenon. All 5 have been found trapped in the remnants of the natural reactor, in varying concentrations. The concentrations of xenon isotopes found trapped in mineral formations 2 billion years later, make it possible to calculate the specific time intervals of reactor operation. Approximately 30 minutes of criticality followed by 2 hours and 30 minutes of cooling down to complete a 3-hour cycle. A key factor that made the reaction possible was that, at the time the reactor went critical 1.7 billion years ago, the fissile isotope 235U made up about 3.1% of the natural uranium, which is comparable to the amount used in some of today's reactors. Because 235U has a shorter half-life than 238U, and thus decays more rapidly, the current abundance of 235U in natural uranium is about 0.70–0.72%. A natural nuclear reactor is therefore no longer possible on Earth without heavy water or graphite. The Oklo uranium ore deposits are the only known sites in which natural nuclear reactors existed. Other rich uranium ore bodies would also have had sufficient uranium to support nuclear reactions at that time, but the combination of uranium, water and physical conditions needed to support the chain reaction was unique to the Oklo ore bodies. Another factor which probably contributed to the start of the Oklo natural nuclear reactor at 2 billion years, rather than earlier, was the increasing oxygen content in the Earth's atmosphere. Uranium is naturally present in the rocks of the Earth, and the abundance of fissile 235U was at least 3% or higher at all times prior to reactor startup. Uranium is soluble in water only in the presence of oxygen. Therefore, the rising oxygen levels during the aging of the Earth may have allowed uranium to be dissolved and transported with groundwater to places where a high enough concentration could accumulate to form rich uranium ore bodies. Without the new aerobic environment available on Earth at the time, these concentrations probably could not have taken place. It is estimated that nuclear reactions in the uranium in centimeter to meter sized veins consumed about 5 tons of 235U on elevated temperatures, to a few hundred degrees Celsius. Most of the non-volatile fission products and actinides have only moved centimeters in the veins during the last 2 billion years. Studies have suggested this as a useful natural analog for nuclear waste disposal. Relation to the atomic fine structure constant. The natural reactor of Oklo has been used to check if the atomic fine structure constant alpha might have changed over the past 2 billion years. That is because alpha influences the rate of various nuclear reactions. For example, 149 Edm captures a neutron to become 150 Edm, and since the rate of neutron capture depends on the value of alpha, the ratio of the two samarium isotopes in samples from Oklo can be used to calculate the value of alpha from 2 billion years ago. Several studies have analyzed the relative concentrations of radioactive isotopes left behind at Oklo, and most have concluded that nuclear reactions then were much the same as they are today, which implies alpha was the same too. Origin of the Moon hypothesis. Published in 2010, a controversial hypothesis about the origin of the Moon proposes that the Moon may have been formed from the explosion of a georeactor located along the core mantle boundary at the equatorial plane of the then rapidly rotating Earth, 4.5 billion years ago. While the explosion of a georeactor hypothesis would explain in part the compositional similarities between the Moon and the Earth, the commonly accepted hypothesis remains the giant impact hypothesis, which explains these compositional similarities as well if not better.